all of my notes. So
that's fine. I think it's okay. It's already okay. Let's keep the way. Is it okay? Let me share my screen. Okay, are you ready? Let's start.
Yes.
Okay, welcome to this World River and Delta Source to Sink series. And today we are very happy to invite Professor Gail Kineke from Boston College come here talk about fluid mud. So today is number 30 in 2021. So as you know, in 2020, we have 35 webinars. You know, now so far, this is number 65 total. So it's all archived very well on our YouTube channel. So before I introduce Gail, as always, I want to mention the next week. So we have 2 more talks, and one is coming from Brazil, University of Sapporo. So Michelle, he will talk about the southwestern Atlantic margin, and also Carl Static used to working as a Kiel University, now retired in Poland. He will talk about the São Francisco River Delta in Brazil. So next week, the topic, we shift to South America. Of course, today, Gail also talk a little bit Amazon. So please mark your calendar next Wednesday and Friday with 2 great talks coming. And so Gail is, as I mentioned, is a professor from Boston College, the Department of Earth Environmental Science. He's used to serve as department chair. And Gail graduated from Princeton University and get her master and PhD from University of Washington. And as here you can see, she postdoc at Woods Hole and just 2 or 3 years in South Carolina, then go to Woods Hole and then all the way to Boston College until now. So Gail's expertise is coastal and estuary process, particularly the fine sediment transport, the fluid mud. She is very active. She working in Gulf Mexico, the Gulf Alaska, and southeast US, Chesapeake Bay, York River, New England area. Internationally, he working, Amazon Shelf, Papua New Guinea, Bay of Fundy, Berhad Sea, Adriatic Sea, Mediterranean Sea, and as soon as there's the fluid mud, I think she followed the mud, and she also the recipient of NSF earlier career award and also when a young investigator award. So I think we're really looking forward to her talk. I believe he will give a little bit overview or review of the fluid mud of her lifelong study. Okay, Gail, now you can share your screen and put precision mode.
Okay, so I hope you can see it. So I thank you for that nice introduction. And again, I want to say a big thank you to Paul for hosting and maintaining this seminar over a very challenging year. And it's just been great. So I really appreciate being able to take part in it. So I am going to be focusing on fluid muds, and I guess I have to say that I'm just going to add that I've been stuck in the mud for about 30 years, and so you're going to be getting sort of a retrospective on that, and that I've done all of this work with a whole lot more than a little help from my friends, and I'll try to acknowledge them. I couldn't do them all justice by any means, but I'll try to acknowledge them as I go along. So we've been talking about source to sink. This is one of the various sketches that you can find describing this. And I'm really focusing on this part on the continental shelf. And we can think about all of the processes that occur there from this figure from Nitrauer and Wright. And this is also the cover figure on Don Wright's book on morphodynamics of intercontinental shelves. And that gives us an idea of, delivery by plumes and action by waves and, all of these different processes. About the same time that this Nitrauer and Wright paper came out, they also collaborated on a paper, Wright and Nitrauer, and they outlined, this conceptual diagram of different stages of dispersal of river sediment in the coastal ocean. And so you can see, I hope you can see my mouse, supply by plumes and initial deposition, and then resuspension and transport primarily by waves and currents. And then, there's this smaller arrow here, which represents the gravity flows. And this has gotten a lot of attention then in, I'd say, since about the mid 1990s or so. And a lot of it sort of started with this image or this illustration from one of Don Wright's papers, again, and this is off the Hoang He Delta in the early 90s. And there was, I remember one of my very first AGU meetings, hearing Don give talks about work off the Yellow River and these just incredibly high concentrations. And, it seemed sort of like such a unique situation. And he introduced us to these, these hyperpycnal flows and gravity flows of these high concentrations of sediment. And my first work was in San Francisco Bay, and we didn't see anything like that. But then just by a lot of luck and being in the right place at the right time, I got to work on the Amoseds project for my PhD work. And that opened up a whole new world for me about transport of sediment on continental shelves. So some of the, I'd say some of the motivation that has been sort of a thread through a lot of the environments that I've looked at is that there's often a mismatch between the visible surface plume and the depot centers on continental shelves. And this is just an illustration. I'll show you, a better satellite image in just a minute. But, when we look at it, there's only about 5% of the transport that's of the sediment that's leaving the Amazon River mouth is actually advected in the surface plume, the visible surface plume that's so dominant in satellite images or even aerial photographs. And most of the accumulation is actually occurring seaward of where that surface plume is located. We can also look at the Eel River shelf, a lot of work done by the Stratiform group. And in that instance, the discharge events, the big sort of flood events that are delivering sediment to the shelf occurred during downwelling conditions where the surface plume is sort of plastered up against the coast. And the flood deposit, which has been well documented, is actually located, seaward of where the extent of the surface plume is in something like, 60 to 90 meters depth. We can also look at environments like some submarine canyons. The CPIC is one that I worked on, where depending on the season, the plume can be going off to the, to the northwest or the southeast, depending on the monsoon season. But most of the sediment, again, like 85% of the sediment that's being discharged by our estimates is going down the canyon. Now, some of that gets transported in sort of mid depth or intermediate depth nepheloid layers, but most of the sediment is not going where this visible surface plume is going. And then one of my favorite systems, of course, is the Atchafalaya, which is a little different, again, in terms of if you look at the surface images, looks like when these cold fronts pass, the plume and is sort of headed more offshore, where some of my results have shown that during these cold front passages, a lot of the sediment actually gets transported onshore and sometimes, up onto the beach itself. So related to that, people have talked about, the mid-shelf mud deposit or a mud belt. And there's been, Paul Hill in a really excellent review paper sort of reminded us of those ideas with, this idea of Swift in 1970 that you'd have, rapid sinking from the surface plume and then diffusion from that inner shelf area to deeper areas where the mud is located. Or McCabe in 1972, that it was just advection in the bottom boundary layer by currents, or Moore in 1969 suggested that there was seaward transport in the wave boundary layer in wave-supported gravity-driven underflows. And, I think that a lot of us were more or less unaware of that until projects like Stratiform or Amosets that really emphasize the point that a lot of the transport is happening not only close to the bottom, but is happening cross shore, which is not compatible with like the mean current transport. So I'm going to be talking about fluid mud. I'm talking to a general audience. I'm not really focusing this for people who are fluid mud experts, and so a lot of this may seem pretty basic to those of you who are familiar with that area. But we're talking about dense suspensions of fine sediment, and it's characterized typically by the presence of a ludicline or a sharp gradient in suspended sediment close to the bottom, and the concentrations are greater than about 10 grams per liter. And I'm going to be talking units of grams per liter, which are equivalent to kilograms per meter cubed. And the definitions are tricky, and in terms of whether it's greater than 10 grams per liter, ludiclines can start forming around 2 grams per liter, but you're on the order of gram per liter concentrations. And the other thing is that fluid muds then can influence the flow through altering the viscosity of the fluid. You can see the viscosity can increase by 10 or 100 times, order 10 or 100 times that of seawater, and through stratification effects, suppressing turbulence. And as fluid muds relate to transport on the continental shelf, we've seen them referred to as high concentration bottom suspensions, sediment gravity flows, wave supported gravity flows, current supported gravity flows, wave current supported gravity flows, critically stratified flows, hyperpycnal plumes, and hyperpycnal flows. Phew. But those are all related, and whatever we want to call them, we may be emphasizing, either how they're formed, how they're transported. But these are all, they're not all the same thing, but they're all related. And I want to reiterate that when we're talking about fluid mud, we're emphasizing that it is a fluid, that it won't maintain its shape outside of a container. So it's not the yogurt-like stuff that comes up in the bottom of a box core. And that it's mud. And so it's fine sediments, mostly fine silts and clays. And so the properties of cohesive sediments are very important in how fluid muds behave. So I always have to go back to the Amazon. That's where it started for me. And I think that there's a lot that we learned from the AMASETS project in the late 80s and 90s. And so on the left, you can see this, I believe it's MODIS image. And, you know, you have a lot of clouds here, right? Sort of what I'd like to be able to see is sort of the front or the edge of this muddy surface plume. We have an older image of AVHRR, which emphasizes the turbidity in the very surface waters. And you can see this, you know, sort of clear front along the edge of the freshwater plume that's coming out from the mouth of the Amazon. And from work in the mid 80s, Kiel and Nittrauer identified this area where the, this doesn't show up very well, but that says 2 to 10 centimeters per year accumulation rates, which are very, very high. I mean, work on, say, you know, that Nittrauer did way back on the Washington shelf, it was maybe, if I'm not mistaken, something like 5 millimeters per year, and that's a pretty healthy accumulation rate. But you notice that the area of this, of the high accumulation rate, which also sort of corresponds to, you know, the, you know, sort of the foresets, the outer top sets and foresets of this cliniform feature is removed from, you know, where the surface plume extends. But if we look at what the sediments look like close to the bottom in suspension, we can see these big expanses or extensive coverage by fluid muds. And so I'm using that 10 gram per liter concentration as my condition for fluid muds. And the copper colored area outlines areas where we always saw fluid mud. So we did 4 research cruises at all different rising, high, falling, and low discharge conditions, different, you know, different seasons. And they're not big seasons on the equator, but we do have stronger energy due to the northeast trade winds, and et cetera. But so the copper region outlines areas where we always saw fluid muds every cruise. And the darker color outline shows where they were thickest. And the green is the 24 PSU bottom salinity contour. And that represents essentially the location of the salinity front on the Amazon shelf. And I'll show you that in a little better illustration in just a minute. And these are, I should have mentioned, these yellow are is the bathymetry. This is the 100 meter isobath here. So the first question is, you know, how did we know that they were fluid muds? And the first thing is that we sampled right through them. And this was a little different because the echo sounder on the ship would give us a water depth that was 1 to 2 meters shallower than what we were able to drop our instrumented tripod, also known as gafanhoto or the grasshopper in Portuguese. And so this was an instrument, that we built at the University of Washington when I was a grad student with Rex Johnson and Dick Sternberg. And as a Marsh McBurney electromagnetic current meter, a CTD, and this pump system where we were able then to collect samples from this nozzle in situ water samples 20 centimeters off the bed. And here the bed is defined as where the tripod stops. And that's roughly about the same as kind of the strength of the sediment that was retained in the top of the box course. That wasn't by design, but by different ways that we tried to determine that. That seems like a pretty reasonable estimate. And so here's an optical backscattering sensor here. So here's a typical profile from, from the old days. I wish I could say that I'm much better at making nice figures now than I was then, but I don't know if that's really true. But we have the depth of the water on the y-axis. Here's the suspended sediment concentration in grams per liter. So we're up to about 200 or 300 grams per liter at the bottom. This is the characteristic ludicline. This is velocity in centimeters per second. And then here's salinity and temperature. And so we were able to, where these dots are, we collected water samples. So we were able to calibrate the optical backscattering sensor to very high concentrations and identified sort of this dual response at high concentrations where the OBS actually records lower than the linear response at lower concentrations. And so we knew that we could see that we were in this example, 2 meters of fluid of a high concentration suspension. Whereas again, most of the time the echo sounder would tell us that this was the bottom. This level at the ludicline was the total water depth. And we also noticed then the salinity, often we'd see this anomalous salinity within that fluid mud layer, that we'd see much lower salinities than the overlying water. And part of that is, a lot of conductivity sensors can get clogged with mud. And so you would expect that you might see lower salinity. But because we had those water samples, we could also centrifuge off the water and test just the salinity. And we were indeed seeing lower salinities in that layer than the overlying water. And we would often also see a different temperature signal within the fluid mud layer than the overlying water. So as I go along, I want to try to point out how we, fluid muds in many environments are very ephemeral. They can also be very thin, but there are always sort of these clues on whether or not they're present. And these were the big clues that we had on the Amazon shelf. We were able to sample right through them because they were so thick, on the order of the tidal boundary layer. And we were able to sample the high concentrations, and we would also see these anomalous signals in salinity and temperature. So we were, when we started the project, we were interested in looking at suspended sediment transport. And here's the Rouse parameter, and here's a figure from a textbook, waves, tides, and shallow water processes. And typically the velocity profile would, we could use the law of the wall. This would be the Kármán-Prandtl equation. And then depending on the settling velocity, you might have a suspended sediment concentration profile that looks like this, with the gradient close to the bottom if the settling velocity is high, and then more homogeneous if the particles are smaller and you have lower settling velocities, and they result in these flux profiles as well. But on the Amazon shelf, this is typically what we saw in terms of, here's the current speed and here's the concentration. I have them in reverse order here, unfortunately. And the current speed does not look like this logarithmic increase away from the bed like the law of the wall. And the concentration profile doesn't look like either the concentration profiles you'd expect from, a higher particle settling velocity versus a lower one. And then here's another example showing that salinity and temperature anomalies within this high concentration layer. So, here's the ludicline. And so the question is, how does it form? If sediments are being resuspended by currents, you probably expect these Rouse type profiles. If it's resuspended by waves, you could typically resuspend sediment up to, you could have higher concentrations, but within the wave boundary layer, so like order of a few centimeters. But again, that's not what we were seeing on the Amazon shelf. Okay, So this is a cross-shore transect on the Amazon shelf. And there's a lot of information here. And but this really encapsulates sort of the story on the Amazon shelf. Here are, in white are the salinity contours. And so at a first glance, if you looked at this and you didn't know what the water depth was, you might think that this was from an estuary, from a partially mixed or salt wedge estuary with very strong density gradients in this cross shelf direction. We've got the surface plume that's flowing along the shelf, which is indicated by these X in the circle symbols. But because of the strong density gradients, we have an offshore flow at the surface and an onshore flow at the bottom. And this is also enhanced by Ekman transport. Even though we're close to the equator, the strength of the longshore winds drives this onshore flow at the bottom. And we see these concentrations of 10, here's the 10 gram per liter and 50 and greater grams per liter. And you can see how the salinity contours wrap around with lower salinity within those layers. So the lower salinity indicates that the fluid mud layer there actually formed closer to shore and migrated seaward. So we have trapped that lower salinity water within the fluid mud layer. If it was resuspension by currents, you would expect the muds to have the same salinity signal as the overlying water, and it doesn't. And you might also think that, well, if you're building up these dense flows, then they should flow offshore. And in fact, they do. With Dave Cashone had a tripod out here that experienced about a 60 centimeter per thick flow. We could tell by it buried the 3 Marsh McBurney's current meters as it went through, and then it sort of deconsolidated. But this was like a single instance that we were able to document but then as we looked at data from all of these transects, we're looking at this profile here would be typical of, oops, missed my marker. So approximately 14 meters water depth is right about here. And you can see the mean profiles. These were at 2 different times of 2 different sampling times. And so a 25-hour mean of velocity is shown here in the dashed line. And that demonstrates the offshore flow at the surface and onshore flow at the bottom. Yet at another point in time, we saw this offshore flow at the surface. It comes to 0, changes direction, and then changes direction at the bottom at about 2 meters at the height of the fluid mud, and had an offshore flow of about 5 to 10 centimeters per second. So over, averaging out the tidal flow, we were seeing this offshore flow within the fluid mud layer. So this, I think in the way people would refer to it today, this is, a shelf front fluid mud. It's forming due to trapping at a density front, at a salinity front, not unlike trapping in an estuary at a turbidity maximum. And the fluid muds are maintained by the turbulence in the tidal boundary layer. And they can persist, and they're partially maintained on the shelf by this upward, both the residual current due to the density differences, but also this enhanced upwelling due to Ekman transport. And when that's relaxed, when these trade winds relax, this onshore forcing relaxes and can allow for these fluid muds to flow offshore. So we learned a lot from that, and I guess this comes back to some of the reasons why fluid muds are important. On shelves, they're important for oil and gas exploration, but also whether or not carbon is being sequestered on shelves in the deep sea. And so on the one hand, fluid muds can be a conduit for transporting sediments and organic matter into deeper water. But in this case, in the strong tides and mixing, they also can be a means for organic matter to be remineralized and reintroduced into the water. So whether they're a sink or just sort of a stopover, and this is what Bob Oller's fluid mud reactor discussion is about, is when you've got this organic matter that's being mixed continuously in these thick layers, you can decompose a lot of the organic carbon. So I just wanted to bring this up now. These are results from a model by John Trowbridge. I won't go into the details. It was a 1D model using the data from our hundreds of profiles on the continental shelf. And this is essentially a normalized suspended sediment concentration profile. And there were essentially two conditions that the model pointed to. And one is where if the free stream velocity was greater than twice this buoyancy anomaly, twice the square root of this buoyancy anomaly, you tended to have fluid muds that looked like this, and it affected the this is, sorry for the interruption there, the velocity profile looked like this. If the free stream velocity was less than that, then the shape of the concentration profiles and the density profiles changed. And this is based on a critical gradient Richardson number condition. And this will come up again. But essentially, if the free stream velocity is high enough, then the fluid muds, and let me start again. If the free stream velocity drops below a critical value, then the fluid muds start to settle out, and you get what I used to refer to as a stratified fluid mud, where you've got 100 gram per liter concentrations, multiple ludoclines, so 100 gram per liter concentrations overlain by another fluid layer of tens of grams per liter. And in the tens of grams per liter, the flow, they're still being mixed. The flow is still turbulent. If the free stream velocity is greater, is higher than this critical value, then the fluid muds look like this. They're like a well-mixed layer, and the flow is turbulent within the fluid mud. So here's some of the questions as we might look at other environments. It's, how do we know it's there if you can't actually sample through a 2 meter thick fluid mud? If you're looking at fluid muds that are only tens of centimeters thick, how do you know that they're there? What are some of the clues? And, sort of what are the necessary ingredients? And so you can have sediment discharge from rivers, you can have resuspension by waves, and then how do you trap it? How do you form it in this fluid mud? And this can happen at fronts, can be settling into a wave boundary layer. And what are the conditions then for it to flow downslope? Well, it has to be, here's the Chasey equation. So you've got the thickness, the density anomaly, and the slope. So it has to be thick enough, dense enough, and steep enough to flow down slope. But then, for example, in the case of the Amazon, there's also this other forcing of this Ekman transport, and this really strong density gradient that would tend to keep the fluid muds on the shelf, on the very gentle slope of the Amazon shelf. So I have worked in a bunch of places. I haven't worked at all the ones that are shown here, and this is not exhaustive for all places around the world where you would find fluid muds. Here's some of the different types that I outlined, sort of the shelf front or pro-delta, event-driven, submarine canyons in Taiwan and Papua New Guinea. And hyperpycnal flows may be the Copper River. There's some evidence that data I have that would indicate they could, you could have hyperpycnal flows from the Copper River or Joklops off of Greenland. And so the places that I'm going to try to get to today is some examples from the Eel River. I've already talked about the Amazon, these pro-delta environments like the Po, the Huanghe, and potentially the Mekong, the Waipo and the Waipu. So we can look not long after the Amazon work, a work by the Stratiform group, including Peter Tchaikovsky, Rocky Geyer, and Andrea Ogston, identified and explored these event-driven wave-supported gravity flows. And so here's sort of the conceptual picture where you've got a sediment-charged river plume with rapid settling out of the plume. And it's in a high energy environment. These flooding events are related to these big storms that come across the Pacific. So you've got long period waves, and the sediment gets trapped within these wave boundary layers until either the wave energy dissipates and the muds are no longer kept in suspension in the wave boundary layer and can flow down slope. And so I just wanted to, ask that question. Well, how do we know? We hadn't really been thinking about these gravity flows or had much evidence for them. And this is from Peter's paper, Peter Tchaikovsky's paper in 2000. And he had an ABS, an acoustic backscattering sensor, and you could see the wave. This is the significant wave velocity in blue in the middle panel, and the river discharge in red. And you can see these events where the warm colors are showing higher concentrations of suspended sediment. And so we know there was a lot of resuspension and high concentrations, but one of the clues that these that they were actually gravity flows was with these individual velocity sensors that were mounted on a tripod. On the right is a typical current event with low waves, and you've got sort of this offshore velocity profile that looks like the law of the wall. Whereas during these other events here, you can see here are the velocity measurements, and the lowest sensor is actually indicating offshore flow. And so that's sort of indicative that there's this lower layer that's flowing downslope. There were also clues in time series that Andrea Ogston collected. I'd bring your attention to this event on the right here. This is days, and we're looking at the bottom velocity, the significant waves, the longshore velocity, cross-shore velocity, mean velocities, and then this concentration in grams per liter and temperature. And you notice, during a lot of these wind events, you can see sort of the resuspension of sediment, that corresponds with either waves or waves and tides combined. You see this event here with very high concentrations. The OBS is essentially maxed out here. But then you see this big drop. And this is a different event, but we can see that in this image where the lowest velocity sensor is here at 10 centimeters above, and the light gray is higher. And during this time period here, you notice that the lower sensor is reading a lower suspended sediment concentration. And this is that effect of the OBS that can read lower during high concentration occasions. And so that was a clue that there was this high concentration layer of at least 10 centimeters thick. And Andrea also had an echo sounder on that tripod. And so you can see, here's the echo sounder. It's kind of noisy during some of the events, but right here, you see this, the altimeter is essentially reading the bottom is higher by some, 10 centimeters. And so those are, sort of the different pieces of evidence that you can sort of tease out for these intermittent or ephemeral events. Well, since then, a lot of work has been done on a number of shelves around the world. Here's an example from the Waipoa shelf, Rip Hale and Ogston and others. And then there were a lot of people who also worked. Julia Moriarty did some modeling, Beaver, Tara Niskern, Aaron Beaver. And so you've got these high discharge events from the Waipoa that can be high enough to be hyperpycnal, meaning greater than 25 grams per liter or so, but the sediment gets deposited within Poverty Bay, and then it's not moved offshore. I'm sorry, Poverty Bay is right here, up in here, and then there are sort of these depot centers that are offshore. And so here's some data from one of those experiments where you can see with this, following this discharge event, and you have this wave event with this resuspension and then transport to offshore. So here's some of the figures from the modeling that he did. And there's also then to the north, there's this river, the Waipu, with a much steeper slope. And you have these combined current and wave supported gravity flows. So all of these different conditions where you've got high river discharge supplying the sediment, but then the transport to deeper water is really dominated by these wave resuspension events that are followed by cross-shore transport in these bottom fluid mud flows. Okay, so I'm going to try to jump to the situation with sort of these pro-deltas and give a couple examples there. Have to, again, sort of pay homage to Don Wright, because he made a lot of observations and did a lot of work with Carl Friedrichs on fluid mud flows and had a lot of this stuff figured out before I ever went to the Amazon. So in the 80s and 90s, Don's work, as I mentioned before, he made these observations of fluid muds and these, I think, was one of the first to be referring to hyperpycnal plumes, and that's where the discharge from the Yellow River was on the order of 20 to 40 grams per liter, which is dense enough to essentially exit the mouth and flow down the slope. I just want to point out that when he was doing the work, the outlet, the main active channel for the Huanghe was this lobe, the Qingxuigu lobe. In 1996, that was diverted, and this is the active mouth now. And the water and sediment is very highly regulated from controls on reservoirs upstream. But we can look at the Po. Not long after this stratiform work, Carl Friedrichs and Malcolm Scully did some work on the Po. And this is in the northwestern part of the Adriatic. So it's a semi-enclosed sea. And this is, the Po is just south of the Venice Lagoon, a bit south of the Venice Lagoon. And this shows the flood deposit thickness of the Pila and the Tole, were the active distributary channels. So Carl and Don Wright and Malcolm used, sort of this force balance, and with this condition that the concentration within the fluid mud layer is dependent on this critical gradient Richardson number. So it was sort of along the same lines that John Trowbridge did, but essentially in the modeling, Friedrichs and Scully would say that the concentration within the bottom layer is set by this critical Richardson number. And so that it's, supply limited there, or it's assuming that that the supply of sediment is great enough to be able to maintain that layer. And here's some of the results showing the area of the deposit thickness based on a distribution of input to the different distributaries of the Pila and the Tole. And they get pretty good agreement with what's observed. And I wanted to mention this one in particular because then they took this modeling with periods of high discharge and no waves, and high discharge with waves where you do have gravity flows, and then sort of projected that over 140-year simulation. And so it's like taking this fluid mud modeling and transport and projecting it into the future to get see the geomorphic response, and they can reproduce this typical cliniform structure. Tchaikovsky also did some modeling, and he directly had observations of fluid muds occurring, and they would account for some offshore transport, but it was small relative to the dominant alongshore transport, just due to currents. So I wanted to mention also the pro-delta as another pro-delta example, the Mekong, and the papers that came out in a special issue of Oceanography. I was not involved with this work. I wasn't involved with Po work either, but I wanted to mention, this is the sediment exiting the Po is deposited during low energy. And so and then it gets reworked, and some of it gets transported back into the mangroves at other times of year. Now, this was another sort of nice multi-investigator investigation. And so, with NITRA and DeMaster, you can have these accumulation rates, and the highest accumulation rates were on the foreset beds at 12 to 16 meters depth. And the reason I bring this up is that Nitrar and Emily Idem, I think, suggest that there may be fluid mud transport, but they didn't directly measure any concentrations that were 10 grams per liter or higher. And the reason I mention this is then I was looking at it, and I came to the just the back of the envelope calculation, that you would need the plume to a surface concentration of 160 or so milligrams per liter to essentially be located over the foreset beds constantly to be able to produce those accumulation rates. And that just doesn't happen. And so in my opinion, the only way that you can get the delivery of sediment to those foreset beds is through high concentration gravity flows. And I think they're there. I just don't think they just didn't happen to be measured during the period of time during these experiments. And they may be very thin also. Okay, so I'm gonna, I just wanna then, I mentioned Don Wright's work. I wanted to mention some more recent work that I'm involved with my graduate student, Michelle Mullane and Jeff Nitrower from Rice, and a number of other people as part of a coastal seas project. So since 1996, when the river has been diverted, this Chingshui-Go lobe, this has retreated about 14 kilometers, very rapid retreat, and there's infilling in the abandoned channel, and Brandy Carlson spoke on that a few weeks ago. So the active channel is here, and so the water and sediment discharge are highly regulated. The concentrations, the water discharge since about the 1960s is down by about an order of magnitude. And the sediment, it's still putting out a lot of sediment. The concentrations are typically on the order of a couple hundred milligrams per liter. There is potential for hyperpycnal flows during these big sediment releases from the Chaelundi Reservoir. And we were hoping to capture that on several of our field seasons, but due to droughts, those releases didn't happen while we had instrumentation out. But one of the questions that we had was, well, even without the sediment release, do you have the potential for these gravity flows? And here's a similar setup as Wright and Friedrichs, and using some of the conditions from John Trowbridge's work. And the result was that off the active delta, very steep slopes due to sediment being deposited in a low energy environment. The slopes are steep enough that there's the potential for flow. And based on dual frequency echo sounder that's shown on the bottom right, we found a difference between the two returns, which is often indicative of a fluid mud. And I put up this, the yellow warning sign that the difference in return from the echo sounder does not always mean fluid mud. It can be an unconsolidated mud over more compact mud. But again, we used one of these tripods with a pump sampling system on it. And we were able to actually obtain an in situ water sample from within this layer of about 14 grams per liter. And so we looked at sort of this is sort of the minimum angle required for a gravity flow. And these circles represent a different layer thickness based on the dual frequency echo sound. So even without a sediment release, there's still the potential and evidence that these gravity flows are occurring off the active Longhoe River mouth. We also then looked at, we did sort of a summer and a winter seasonal comparison. And the story here is that in 12 meters, right off here, in about 12 meters water depth off the active river mouth, in the winter, we were seeing significant wave heights in these different wave events of up to 4 meter waves. And so we were seeing, suspended sediment concentrations of 1 to 2 grams per liter, a half a meter above the bed. That's very high, so there's good potential for fluid mud. And then I would also suggest that then in this period here, the tidal currents were strong enough compared to non-wave conditions in the summer. These tidal currents were strong enough to cause tidal resuspension, but essentially we don't see it. And to me, that says that there's probably a ludicline during this period that was formed from the resuspension and settling from all of this wave activity. And then due to the ludicline, the tidal currents are not able to resuspend sediment or break down that ludicline. And then the story in the winter is that here's the fluxes in the summer. Mean flux is over about a 2.5 week period. And then in the winter, we see this significant offshore transport due to the higher resuspension and potentially formation of the sediment gravity flows. Okay, so I'm not able to go through the Atchafalaya story, except that there's in the winter, it's driven by these wave events, and we form the combination of newly delivered sediment, which is shown in these inventories of thorium, I believe. We can see the delivery of fresh sediment and sort of onshore transport. And I'm going to just emphasize that in this one wave event, I'm going to skip. This is data that Peter shows, or from Peter's paper, Peter Tchaikovsky. You see a lot of resuspension, and then as the wave event is declining, you see sort of the formation of this big interface. And this is the ludicline. And if you look at the attenuation rate, you see this, it's essentially a normalized attenuation. You see this highest attenuation rate associated with the formation of the fluid muds. And so I'm gonna skip that, but the indication is that with the formation of the fluid mud, you have onshore transport interrupted by some offshore periods of offshore transport. So this is data from a PCADP. This is current velocity. This, the black line is the mean location of the ludicline, and you can see strong onshore flow within, right above the ludicline. And then this blue period is offshore, weak, low flows, but weak offshore flow within that fluid mud layer. So I highly recommend Peter's 2015 paper. These are some of the only direct measurements of velocity that I've seen in fluid mud flows, that are thin, like on the order of tens of centimeters thick, and not big tidal flows, not big, 2 meter thick fluid muds that we see off the Amazon. So I made some estimates about concentrations, and I'm going to skip that and the periods of offshore flow. And I thought that I would sort of wrap up by taking a look back to a paper that Don Wright, a review paper that Don Wright wrote in 2006 for, actually it was a an issue, special issue of Continental Shelf Research honoring Dick Sternberg. And, these were most of the key points that that Wright made at the time. So this is in 2006. It was after his work on the Huang He, excuse me, after Amoseds, after Stratiform, and sort of about the time of some of the work on the Po. And here's some of the points that the river discharge does not need to be hyperpycnal to drive gravity-driven sediment flows across continental shelves. And I think this is important because, it's almost anywhere you go, if you have, adequate sediment supply and big events that can resuspend a lot of sediment at the same time, you have the potential to form a fluid mud. There's little evidence that hyperpycnal river effluent traverses shelves uninterrupted. The exceptions may be where Submarine Canyon enters the river mouth and the slope is steep enough. So I think we do have some examples of this in the CPIC and canyons, submarine canyons on the west coast of Taiwan. The largest river systems are strongly hypopycnal, meaning surface plumes, but this does not preclude the dominance of gravity-driven transport of highly turbid layers. And I think we have many examples of that today, many more than we did in 2006. And that these fluid mud layers are maintained by wave or current-induced velocity shear. And without that shear in the boundary layers, the transport would be brief and dispersal distances short due to the low angle of most shells. And we can explain the emplacement of flood deposits on sort of these mid-shelf mud deposits or flood deposits due to this wave and current supported gravity-driven transport. And that the delivery of sediment cross shelf via fluid mud flows may be a control on the large scale formation and morphology of these cliniforms on shallow shelves. And so he then suggested these 3 items as future topics. And so I sort of thought I'd end with this, so how are we doing? And, he said the area of future research was kind of quantitative relationships for shelf morphology due to gravity-driven transport. And I would point to the Friedrichs and Scully work on the Po, and there are other examples where they're relating gravity-driven flow to the morphology. The internal structure of wave-supported gravity flows, including boundary conditions. I mentioned Tchaikovsky's work off the Atchafalaya. He's got just really incredible measurements. So we're getting to estimates of viscosity measurements indirectly through his instrumentation and observations there. And then conditions for initiation and extinction of shelf gravity flows. And so this is where we would get to prediction. And I think that with the increasing site-specific examples, that I kind of envision that we may be leading to sort of a general parameter space where we would be able to make these kinds of predictions. I think that's that there's a lot of work to be done, but I think that's that we have enough. Oh, I shouldn't say enough. You never have enough, but we have many examples now that I think we could cover a pretty broad parameter space to be looking at those kinds of conditions. So sorry I went over, and thank you very much.
Gail, this is a fantastic talk. And so as our colleague Wei Jun Cai, he has already left. It's a great talk. And even Bob Eller, and he said very nice synthesize, and he also have left for other meeting. Okay, any question from audience? Please go ahead, unmute yourself and go ahead to ask again.
Yeah, can I have one?
Yeah, sure, go ahead.
I just switch on my video. It's more, it's nicer. Just a question about the Po pro delta that you quoted in one of your examples. You said that the tidal forces, tidal currents was generally a condition of having these fluid muds in operation, so that they remain fluid due to these tidal forces.
I'm sorry, did I say that for the Po?
No. You said that in general in your introduction for the Amazon.
Oh, yes.
But yeah. I was wondering if, because I'm working on the Rhone Delta myself, so and you know we've never really considered this fluid mud stuff. But I suppose so. That's my question: are these tidal forces necessary to maintain these fluid muds on their movement, or is that not a condition? For example, in the Mediterranean Sea, which is characterized by these micro tides.
Yeah. So I don't think that the tidal currents are necessary, but I think that they're probably, if you see them, they're going to be associated with wave resuspension events. And so that if the fluid muds are formed, like, you know, rather than just, you know, we have a resuspension event and everything settle out or everything advected away, as the, you know, as long as there's some adequate wave energy, then you've got energy in the wave boundary layer to maintain the fluid mud. And then if it gets dense enough, then it can flow, you know, down slope. But in places where, you know, like in the Mississippi off the Atchafalaya, the tides are very weak, but it's, you know, it's these wave events that can form it. And then if that, you know, it's like, if it gets thick enough, dense enough, or if the slope is steep enough, you know, then you can have it flow.
Well, just as a follow-up, you mean wave energy that's in the like 5-10 meters below the sea level, or even deeper?
Well, I'm saying like the surface wave energy, but depending on, you know, the wave height and period, that's going to determine, you know, sort of the shear and the thickness of the wave boundary layer. And so if you're dumping enough sediment in that and you can sort of keep it with when the energy is declining, your settling flux can be very great, but it can get trapped in that wave boundary layer and essentially be maintained. And sometimes it'll die out, or maybe it'll flow down slope. I hope that was getting at your, so it doesn't need to be tides, but in places like the Amazon where you have really strong tides, I wouldn't have called, like back in my graduate student day, I wouldn't have called them current supported or tide current supported. You know, that wasn't, but when we look back on it now, I think that is an appropriate descriptor after we, you know, started thinking about these wave supported gravity flows on the eel shelf, which came, you know, a little bit after Amazons.
Okay, so Courtney and then Dave DeMoss.
Yeah, can you hear me?
Yes,
I can. Hi, Courtney.
You're not going to see me today, but because I'm not going to turn my camera on. But
not fair,
Gail, and you look fabulous.
Not fair.
So my question a little bit follows up on what Christophe just asked about, which kind of triggering of gravity flow, and when you mentioned Don's bullet list of triggering mechanisms, you talked about the energy needed, but I've also always thought that we should include the availability of sediment, that there
Absolutely.
are places where you don't have gravity flows, even if the energies are high, unless you have a flood event or something that puts in fresh sediment.
I totally agree. And I think that that was a poor delivery on my part if that wasn't clear, because, you know, you need, like, on the Atchafalaya, you know, it's the recent delivery of new resuspendable sediment with the cold fronts that sort of make those fluid muds possible. And I'd say, like, on the on the Waipoa, you know, you have the fresh delivery of sediment to Poverty Bay that can then get resuspended. So I think that's and even on the eel, you know, you need the sediment there that's easily resuspendable to be able to form the fluid muds.
And then I had a question about the Atchafalaya system. Do you guys have you know, the data that you showed from Peter's stuff was at like 5 meters, I think? You said you had to speed through it, but
Yeah, I'm sorry about that.
okay.
We had 3 tripods out at like 4, 6, and 9. I can look back.
Well, my question is, how do you see the gravity flows at the 9 meters or the fluid muds, and more generally, like how deep a water do you think in that system we can have fluid muds or gravity flows?
Oh, I think within 10 meters. I don't think they're getting much further offshore than because, and I think they're, and Peter and I have had, I don't know, I wouldn't say a disagreement, but my earlier work showed the near bottom onshore transport with the reestablishment of stratification, and as a cold front passes. So as a cold front passes, you have offshore flow at the surface and onshore flow at the bottom, right at the time that fluid muds are forming. And so my argument had always been, this is how you can account for this area of accreting shoreline, on this part of the coast west of the Atchafalaya. But Peter sees, these sort of brief periods of one event that I know of offshore flow. So I think that, and Sam Bentley has seen some evidence for offshore flow, but I think that they're more like, I think the offshore gravity flows on the Atchafalaya are infrequent. And for the most part during this system, what's really cool about it is more often you have onshore flow after onshore fluxes after an event, and that the presence of the fluid muds attenuates the wave energy so that it's sort of a natural shore protection. The more storms you have, the more onshore flux at the bottom, and the coast is protected from the wave energy. So that's probably more than you were interested in, but I threw it in there because I didn't finish or didn't get to talk about it during.
No, that's great. But you would say inshore of 10 meters, you think?
Yes, I do.
Thank you. Thanks.
So there's a long way to say, yeah, shallower than 10 meters.
Dave, go ahead.
Sure. Gail, wonderful talk. It's great to see the pervasiveness of these hyperpycnal flows. At one time, we were thinking it was unique to the Amazon, and now in different ways, they're occurring worldwide. My question is, what do we know about the aggregate size in these hyperpycnal flows? And do we have any real measurements? And do you think that they're dependent on the suspended solid concentration or the turbulence, or do they vary from site to site depending on the nature of the lithogenic flux from the river? How variable do you think that is? And do you just model it with one number, or are there variables that cause that aggregate size to change?
Well, I think that to form the fluid mud, you need aggregates. Absolutely. I mean, if you were just looking at the fine sediments, they can't settle. Your settling cannot be fast enough. And so we have from the Amazon, from the Atchafalaya, from the Po, from all, many of these systems, we have particle characteristics in the water column. But once you're within the fluid mud, then I think it's almost anybody's guess for a couple of reasons. One, it's hard to measure because optics don't work, acoustics don't work. It's just the concentrations are too high. And you get into a region of hindered settling, which could be partly because, the particles are, if it's kind of a still fluid mud, like in estuaries forming at slack tide, then you can be forming sort of a card house structure. And so that's like building a network of aggregates. But within the fluid mud, it's, I don't know what to say except that Yeah, I don't know what to say. I think that because in some cases, whatever size they were when they came in, they could be broken up because there could be sufficient turbulence. On the other, you've got often, organics or that they're coming in as flocks. And so I don't know what to say. I mean, typically we deal with like just a, to treat it for transport or whatever, you'd think of it as sort of a representative settling velocity, which is going to be very low. And we look at the behavior of the fluid overall, and we can estimate, we can sort of back out a viscosity, but that would include particle-particle interactions in that estimation. So I think that, so within the fluid mud, I really don't know. And I do think, I remember there were some people at the Corps of Engineers in Vicksburg who were working on sort of mud dynamics and that kind of thing, but I haven't kept up with that that work, so I don't know.
But it's on the order of like 100 microns, or what aggregate sizes are you using for fluid mud formation?
I would say we're seeing, I'm trying to think, like on the order of hundreds, like up to 500 would not be uncommon. And we were seeing maybe 50 to order of 100 or 200 in work that we did off the Hoang He recently and in the Petitcodiac. And that's, I didn't talk about any of the estuary work that I've done, but I'm saying, we probably need aggregates on the order of 100 microns to get the settling velocities necessary to, get a high enough flux to form a fluid mud layer.
Great, thank you.
So it's a great, Gail, before we go, I really have some question to ask you. Just to follow Dave's question, if we get a reverse suspended sample and we get the distribution grain size, then we get fluid mud, the grain size distribution. And if we get the fluid mud sample, bring it to the lab, do a little bit strong shaking, rotation or whatever, physical disturbance. Can we observe they will break up the flocculation, the grain size change, sharply change?
I don't know. I really don't know. I mean, I actually have, I think, 2 remaining actual Amazon fluid mud samples left. And so we could try, or we could,
but let a student run something. I mean, that's something can bring the hypothesis is how much the salt play a role, the flocculation, congregation,
yeah, I don't, yeah, I don't think that I don't think salt matters much, except that it's salty, like once you're into like 2 PSU or something.
Yes, this is bring my second question. If you look at your talk, most of the fluid mud, it looks like on the middle shelf. It's kind of, even Amazon is stopped at what depth, 40 or 50 meters? It's like 10 to 30 meters, right? The yield shelf maybe a little bit deeper to 60 meters. And the Pearl River is 5 to 30 meters. And looks like in that 30, 40, 50 meters, there's no deeper. Most is 10 meter, 5 meter to 30 to 40 meters, that range of the water depth. But remember, the initiation, the onset, the formation help to formation the fluid mud, maybe starting inside the estuary.
Could be. I think that that I'd say probably the other, the third half of my career was spent like in estuaries. And because a lot of the processes there are much more predictable. I mean, fluid muds were initially identified in estuaries. And so I think that so I don't think that salinity is as necessary. I think salinity is necessary to like get things going, but the things that are probably have a bigger control once you're on the shelf or in the coast or like organics or concentration or
biology, some stuff.
yeah. And so I think that like once you're past like the level to form a turbidity maximum, then salinity doesn't really play a role.
So looks like the estuary could be like a manufacturer, when the fresh water meets the salty water, but they flush out to the shelf. But on the shelf looks like some convergent mechanism or gravity, upwelling or whatever, kind of constrain them in that water depth 5 to 30 or 40 meters. But next question challenge is how those flow mud was disintegration, how to gradually disunit and then deposit or charge even further deeper. That's the challenge research.
Yeah. So work that I've done with Tim Milligan in the Petitcodiac River has been great. This was several years ago, but the concentrations were so high and you had tidal cycles, so it was like turning a flume on and off, and we could actually see fluid muds form. And then once the currents picked up again, you could see sort of what that critical shear was at the interface, at the ludicline, to break up the fluid mud. So, but like on the shelf settings, I think that if we look back at the Waipu and the Waipoa and some of the other places with, good observations, that, the fluid muds, we haven't been able yet, to my knowledge, to like ride along with the fluid mud and make measurements, within it. But, you see them passing your tripod site. And so I think that, they, like the fluid muds form through settling, and then they're maintained due to the turbulence. And if the turbulence dies, because the wave energy goes down, then they'll slowly consolidate or get advected, or just get advected. But then if they start to flow, they accelerate with the steepening slope, but they decelerate with, when the slope is decreasing. And that's kind of what Malcolm and Carl did on the Po. And so that the fluid muds will essentially disappear either when the wave energy is gone or if they're flowing when the slope changes.
Thank you very much. I think maybe the next decade we need to work on the Andaman Sea, the Gulf of Martin. I mean, the fluid mud is one of the largest area in the world. Is that right, Courtney?
Yeah. I'd love to. That's why I was so excited.
Don't retire next year. Hold on for 5 more years. Okay, we need to write another proposal.
Well, I was very excited when I saw Steve Keel's talk and Courtney's talk, and there's, sort of these hints that it's fluid mud. And of course, I see fluid mud everywhere. Just like, if you buy a new car, you see the same model everywhere you look. It's like every muddy system I look at, I'm sure there are fluid muds there. So.
Okay, cool. Next talk, you should see the river without fluid mud. Talk about why they don't have a fluid mud. Okay. Okay, cool. I think we have to stop here. Thank you very much. It's a great
Thank everyone for coming.
Discussion. And so, okay, Carl, you will stay here a little bit longer for a test, all right? For your next week talk.
Hey, Gail, thanks.
Thanks for coming.
Hello, Paul.
Hello, Carl. I cannot see you. Did you?
Yes, I have to.
Oh, now yes.
Can you see me now?
Yes, I can.
Sorry, I hear you 2 times. Actually, and what you were talking 30 seconds ago.
Oh, I see a echo. Do you have a 2 device or 1 device? I can hear echo from you also.
Yeah.
Oh, Can you try again? Sound like
Yes.
that. Now it's better.
I think now it's better. Yes,
Yeah, much better. Very
much
good.
better.
Hey, how are you? I haven't seen you for a while. So are you in Poland, right?
No, there's another talk going on.
Okay. So are you in now in Poland, right? You are not in Kiel. You're not in Germany. Can you hear me? I cannot hear you.
No.
Oh, now, okay, now, okay.